All right. Hello, everyone. So, welcome to my stream. Today, I'll be continuing to work on my Vectrex emulator. Last week, when I worked on this, I fixed a bug finally that was in my AND B instruction, where I was ANDing the wrong register, and because of that, it caused the program to go into this infinite loop and eventually access memory in the wrong place. So if you watch the last stream, you'll see that I basically hunted down that bug and was able to fix it. And then that led me to now where I'm at, which is if I run the debugger, I get to another unhandled instruction that I have yet to implement, which is com-a here. So that's what I'm going to be implementing today. So that, excuse me, com-a would be the complement accumulator here. Something in my throat. All right, so let's see here. If we open the CPU opcodes table and look for com, so there's com-a, complement accumulator. So actually what I want to be doing is implementing this complement instruction. There's com-a, com-b, there's other regular com instructions for the different addressing modes for memory. I actually realized that in my table here I have these strings that say accumulator when it shouldn't say. I realized that a little earlier. I have quite a bunch of those that I need to, either I need to remove them all, or what I want to do here is replace this with like memory location. Like in this table, we have accumulator and memory location. So I can either say, change these accumulators to memory location, or just remove them all together, which I'm not sure if I should do that. Yeah, I might. Just looking at the table to see if it would be any clearer or like less clear. Maybe I'll keep it. I'll just correct the ones that are clearly incorrect. Be like accumulator becomes memory location. Or maybe just memory. Let's see here. Like that. Basically, if the instruction doesn't say A or B, oops, unlike that one, com-a, so we'll define illegal, no, decrement A, inc A, test A, clear A, negate B, com-b, dec B, inc B, test B, clear B. Here, negate should be negate memory location. Oops, no, that's correct, yeah. Bit test accumulator is fine. Okay, I think this is good. Okay, so let's work on the CPU here. I like to split opcodes to the side. So we want the complement. Now complement basically is an instruction that, if we look here, complement. Operation O plus the complement of M replaces the contents of M or accumulator X with its one's complement, also called the logical complement. The carry flag is set for 6800 compatibility. That's pretty straightforward. Okay, so let's do this. I want to find all instances of com in this file. That did not work. Oh, because of compare. Right. Match case. There we go. Let's grab these. Looks like it should be all page 0. Yeah, these are all page 0 instructions. So where should I put complement? Doesn't really matter, but subtract, increment, decrement, shifting. Here, let's put it near the shifts, since it's a bitwise operation. Case. So only these two are A and B. I forgot to put template parameters 0, the address, okay. Fred says, it is wise to put it in between the shifts. Thanks for joining, man. All right. Let's implement complement. Let's go up here. So complement follows the pattern of most of these operations. So we start with a version for it, an overload for the accumulators for the 8-bit registers A and B. Where we just want to take the value and set it equal to the complement of the value. Now we want to set the flags. So these are set as usual. We clear V and we just set C. So that's pretty straightforward. Right, so we say CC, waiting for my autocomplete. Doesn't like it. Oh, right. Should rename it. And there we go. So negative will be, what I call it, calc negative of value. We'll set 0. Overflow is cleared, and carry is set. Don't remember if I was using true and false now. 0 and 1. Okay. There's nothing special. Okay, so let's do the one for memory. Okay, yeah, let's read our value. Basically want to perform exactly the same thing, set the same flags. This time it'll use the it's just 8-bit. In fact, I think what I've gotten into the habit of doing is just calling this version here. Yeah, that makes more sense. Which will set all the flags, and then we just do a write back into memory. This follows exactly the same pattern as left shift register here. Okay, this should compile. Or not. Ah, yeah. Yeah, that was something that was bothering me here as well, is that technically speaking, it's weird to be calling the version of this for a different page in opcode when I don't even use the page in opcode. So I gotta think a bit about that. Yeah, I'm not sure I like that too much. Because it means I'm generating a version of this function, although it just ends up being inline, but like it doesn't really make sense. If I wanted to use the page in opcode here, anyway, yeah, I think I remember thinking I'd have to think about this later, because I do it in a few places now. Maybe what I want is, I just want a generalized opcom impl that both call. That's probably what I want to do. But it's okay for now. Okay, so that compiles. So let's see how far we go. Okay, so debugger is open. Load my symbols. Set the dude register to FF, disable trace, and continue. So let's see how far we go now. So now I get another write to ROM not allowed. So historically when I get this, it means that we're writing to an address we're not supposed to, and most of the time that's because there's something that goes wrong in the CPU implementation. Like here, writing to address 1 during an increment. So let's see if we can figure this out. You know what? These copy-paste errors. I wonder if there's any others that would just stand out. Okay, well, I've had one of these before where I forgot to put a break, and so then it runs an extra increment when it shouldn't. Probably on the wrong address. Okay, let's just check here. Yeah, everything looks good. Let's try again. Okay, great. So unhandled operation multiply. So that'll be the next instruction we implement. So before that, let me just push the changes I have so far. Okay, so I'll push this. Correct descriptions in opcode table. And implement complement. Complement, right? Not iment. All right. Okay, so next one is multiply. Let's take a look at what that looks like. So multiply the unsigned binary numbers in the accumulators and place the result in both accumulators. Unsigned multiply allows multiple... Yeah! Hey, thanks for following me, ABDCW. All right, so let's see here. Multiply the unsigned binary numbers in the accumulators and place the result in both accumulators. Okay, so we're going to be multiplying the value in the A register with the value in the B register and storing so this is 8-bit by 8-bit and storing the 16-bit result in both A, B, which I suppose means storing it in D, which is both A and B this way. Unsigned multiply allows multiple precision operations. The carry flag allows rounding the MS byte through the sequence mul ADCA. What does that mean? So if we multiply and then do an add carry in A with 0, add with carry to A with 0. So the carry flag allows rounding the most significant byte through the sequence. Rounding the most significant byte. Not sure why, but okay. If somebody knows why that would be the case. So adding 0 with carry to the top 8 bits of the result rounds it. I don't know. All right, and just to look here, so these are not affected. That said, if all bits are cleared, not affected. And the carry is set if accumulator B bit 7 of result is set. Maybe I don't understand what they mean here. It's an unsigned multiply. See if I can find something on that. Unsigned binary multiplication. Hey Fred, We're back. So yeah, I need to implement this multiply operation. And it says that basically I need to take the 8-bit value in A and B and multiply them and store the result as a 16-bit value in both A and B, which is really D. Multiply the unsigned binary numbers in the accumulators and place the result in both accumulators. Unsigned multiply allows multiple precision operations. The carry flag allows rounding the most significant byte through the sequence mul followed by add with carry A with the value 0. So I don't quite understand, so I'm going to read a bit about what this means. Multiplying unsigned numbers in binary is quite easy. Recall that with 4-bit numbers we can represent numbers from 0 to 15. Multiplication can be performed or done exactly as with decimal numbers, except that you have only 2 digits, 0 and 1. The only number facts to remember are that 0 times 1 is 0 and 1 times 1 is 1. This is the same as logical AND. Okay. Multiplication is different than addition in that multiplication of an n-bit number by an m-bit number results in an m plus m-bit number. Let's take a look at an example where n equals m equals 4 and the result is 8 bits. Okay, they mean a 4-bit number and the result is 8 bits. Okay, so like in our case, it's 8-bit plus 8-bit and 8-bit will make a 16-bit result. So here 1010 times 0110. So 0, 1 times 1. Right, so 1 times 1 is 1. Ten times 6. Okay, that's 10. That's 6, which is 60. Is this 60? Trusty calc. No, that's not right, but I just do. Yeah, so that's 60. I don't even understand what's going on here. So Fred says it's like decimal multiplication. Isn't it 0 times 0 is 0? Oh, right. So it's so 0, basically this 0 multiplied through is this one. Then 1 multiplied through is here. And then this 1 multiplied through. And then 0, and then we add the results. Yeah, okay. There's no chance of overflow. For 2-bit multiplicans, the largest possible product is 225, which can be represented in 8 bits. So, okay. And then there's this property they talk about how you can take unsigned multiply allows multiple precision operations. The carry flag allows rounding the most significant byte by doing an add with carry 0, which is, I don't understand, on A, which is basically taking the most significant byte here and adding with carry. Oh, it's like adding with itself. Is that what it means? No, this is saying add with carry this immediate value. So not sure. Oh, I guess if carry is set. Ah, okay. Okay. Because it's saying that if bit 7, which actually would be in the low byte, if that bit is set, then carry is set. And if you add this guy, just add 0, but with carry, it's like adding the carry if it's there. So it's add 1 if carry is set, or add nothing. So that allows you to round the most significant byte. Right, makes sense. Okay. So, I mean, in my case, for emulating this, I just have to do a regular multiplication, I think, right? And just look at the bits. Oh no, I need to know if the low byte set carry. I guess to know that, I just need to, how do I know? I should look at the bit. Just look at the result. If bit 7 is set, then that means carry is set. Fred says, I think you can simply check that after you compute the 16-bit result. Would have to see the doc again. Yeah, it seems so. It says if the 7-bit result is set. So it's just a regular multiply of two 8-bit values stored in the 16-bit result, and then just computing carry and 0. All right, sounds good. Let's do that. All right, let's look at our multiplies. There's only one. Okay. So let's put this with our add and subtract here. So this is add, subtract, got negate. Yeah, I'll put it after, let's put it after add with carry. Mul. Wait. All right, because mul works on both A and B. ABDCW asks, is the Ergo Pro keyboard any good? It seems kind of pricey. I like it. It uses Alps, like Alps style key, like switches, which is the old Apple style. But Matthias got like the license to make their own. They're not too loud, so it's good for work, but it still gives you the kind of tactile feel. So you'd have to try these kind of keys to see if you like them. But for me, I used to use the ergonomic, the Microsoft Ergonomic 4000, which I liked. I still kind of like the Ergo 4000, maybe a bit more in terms of the way some of the keys were shaped and stuff. But the more recent versions of it, because I think I changed it like 3 times, because after a while those rubber domes really get used up, and it would feel really mushy after a while. And then I bought the latest one. So it used to be like a $60 keyboard, and then it went down to $40. And I totally felt that there was a change in the manufacturing, and I looked into it, and in fact they had changed the way they produced them. The space key, for instance, used to have 2 grooves for the space, and they made it 1. So like now the space key would kind of teeter a little bit. And there were other things. It just didn't feel as good as the older versions. So I started looking into mechanical split keyboards that were standard layout, and this was the only one that I found. I think now there are a couple that have come out. But yeah, no, I'm pretty happy with this. There's a little bit of a learning curve just for the fact that home and page up, page down are situated down here. Let me see if I can show that on the camera a bit. So over here, you've got this like little cluster of 6 keys, the arrows. The arrows are fine, but home and page up, page down at first was a bit weird for me because I was so used to reaching over and using the 6 on the right side. But after a while, I got into the habit of using my thumbs to do page up, page down, and sorry, home and page up, page down. So now I never even look. It's actually fairly comfortable. So yeah, it's I think it's quite a decent keyboard. And actually, I mean, pricey. For $200, it's one of the cheaper mechanical ergonomic keyboards out there. There's quite a price range, you know, depending on what you're looking for. I mean, I know you can get a decent one for like 100, 150 bucks or something, but there are also keyboards that are like 350 bucks. So I think this is decently priced. I know this is not the kind of keyboard you'll find in stores, so it's kind of hard. You can't really try it. You kind of have to know someone who has it. Although I think they have a decent return policy, so I think you just have to pay for the shipping. So if you buy it and are not happy, you can always return it. So I'd look into that. Okay, so op-mul. So I need to take both A and B and multiply them. And let's compute, what was it again? Calculate 0 off this result. Carry. Thinking about my calc carry. Can I even use that? I don't think so. No. Okay, I'll just do it here. Let's check if bit 7 is set. And we write the result into D. Okay. Just going to put a breakpoint. All right, so let's see what happens when we get to the multiply instruction. Okay, here we are. So A and B, oh, there's 0. So that's going to be not that interesting. 0 gets set, carry is not set, and D gets 0. Okay, so now we're getting calls with slightly more interesting values. So 8 times 0. 40. 64. So I must be in some kind of multiplication loop right now. Ah, and we get to the very funny sex instruction. Yeah. Let's implement sex. SEX, which is sign extend. All right, and I think there's only one. This is another one of these. Yeah, great mnemonic. Yeah, I mean they had more, right? They had more characters and CC, but I think that it's always 3 letters for the base mnemonic, and then this is registers. So there you go, sign extend. I've never come across that one in my career, says Fred. Yeah. Yeah, I don't know. What else would they call it, eh? Okay, so let's see. This instruction transforms a 2's complement 8-bit value in accumulator B into a 2's complement 16-bit value in the double accumulator. So basically, we just want to check if the most significant bit, bit 7, is set. Then we want the then we basically want to set A, which is the high order version, into FF. This is what they put here. Yeah, there you go. If bit 7 of accumulator B is set, then accumulator A becomes FF. Otherwise, it's set to 0. Pretty simple. Okay. Fred says on x86, it's move SD, move SXD. Not quite as romantic. Yeah, not quite as sexy, is it? All right. So sign extend. Where does sign extend belong? I'll just put it here. Case. Be funny if would be funny if YouTube decided to delete my or block my upload because of the use of the word sex. Or maybe they're gonna have to put one of those. You need to be 18 and older to watch this this video. You know, dealing with adult material here. Okay. So, if B and bits 7 not equal to 0, A equals FF, or let's do it this way. Okay. And I need to set N right. For that I can just do calc negative on D or A, doesn't matter. I'll do it on D because that's really the result. And Z if accumulator D is clear. The other two are not affected. That should be good. It's called here. Realize I'm not centered in my camera here. That's better. Okay, so let's see what this is getting called on. So every time I play now, every time I run my debugger, it runs for a little longer and longer than before. That's kind of good. All right, so here's the SEX instruction. So A is 127 and B is 0. So right, we're sign extending 0, so A becomes 0. And negative should be 0, and 0 should be 1. Just want to check. Yeah. Okay. And now we stop on another instruction, which is roll A. Fred says, yeah, always super exciting. It's like the law of accelerating returns. Yeah, being able to have it run. Although I have to say, the fact that it runs for so long, so slowly, it's a bit disconcerting. But I am in debug, and it's, you know, yeah. I don't know how much the debugger is getting in the way, so I'll worry about that later. Okay, so we want roll A. Let me just see if I can get an idea of where we're at. E7BF. Does that kind of map to something in the BIOS here? E7, right? Interesting. So if we're at E7BF, this means we're no longer in the BIOS, I believe. Does that make sense? The memory map. So if this is right, it means that we're actually in Mindstorm. Huh. So we might be actually executing Mindstorm, which is the built-in game in the Vectrex, which occupies the first half of this block of memory, starting at E000. So if this is true, that's really, really fucking cool. It would mean that we've finished the BIOS loading routine and that it jumped into the game. But I don't know. I don't know to trust anything yet, so right now I'm just getting unhandled operations and I'm going to implement them and we'll see how far we get. So roll A. So let's just get this committed. So I did multiply in SEX. All right, moving on. So roll is rotate left A, rotate left B, and then we have the ones for memory. just pull that up. Okay, roll. Rotate left. Right. Rotates all bits of the operand one place left through the carry flag. This is a 9-bit rotation. So carry gets put into the least significant bit. The most significant bit makes it into carry. So it's really a rotate left with carry. All right. B8. Okay. Let's do this. CPU. Just delete some breakpoints. So where do I want to put rotate? I think I have some. I'll put it with like the bit manipulations that I have. Like these ones. Left shift and right shift. So I'll put it here. I guess I'll do rotate left and then maybe rotate right. I'll start with this one. Find all. Gotta stop hitting caps lock. Up, ROL. And A and B here. Okay. We'll start with the register version. Okay, so we want to take the value in the carry, and we're going to put that. So let's shift left the value. We need to save off old carry. All right, yeah. So original carry is equal to cc.carry. Then we'll set carry to value in bit position 7. So that's the high order bit. No, sorry. Like this. Okay, so that gets the high order bit into the carry. We have the original carry to put into the value itself, we shift this by 1, or I'll do this. Set it equal to value shifted left by 1, ORed with the value of original carry. You know what? Let's do that. Okay. Yeah, I think I know. I think this is another. This document has mistakes in it. It's probably missing something here. Basically, what it's trying to say here is if the sign changed. So basically, if I think what they meant was B6, B7 probably. And if we rotate, yeah, I think they just mean if we AND the result of the two. So I already have an example of this somewhere. Because basically if it was 1, 1, then rotating left would not change the sign of the value. And if it was, say, 1, 0, it would go from a negative number to a positive number by rotating left, which I guess is overflow, and if it's 0, 1, same type of thing. So basically, overflow is set if overflow is set basically if it's 1, 0 or 0, 1 here. And I think I actually wrote that somewhere here. Might have been for increment actually. No, that's it. This is decrement by 1. Yeah, I think that was the one. Right, because in this specific case, if we were to decrement by 1, it would go from being a negative to a positive. It would overflow. So I guess I could do the XOR of those two bits. See, I bet you they wanted to put XOR of B7 and B6, not B8. There's a lot of tiny mistakes like that, but they kind of matter when you're implementing it. But to me, that would make sense. We have a number. The question, I guess, here is, did they mean for the carry to be part of the number, since we're shifting the carry into the 0th position? It's like all these little mistakes, you know. Here we see B7 goes into carry, then there's a comma. So the next thing is, okay, so the result is B7 and then B7 prime to B1. I don't know. I can't read this notation. Doesn't make any sense. Okay, so I set carry here. Before, I might want to actually set the other values before we overwrite value here. So, okay, actually not for negative. Negative is the usual. So Fred says, in case this helps, on the Game Boy there are two forms of rotate instructions. Rotate through carry, which treats the carry flag as an extra bit in the register, and straight rotate, which sets the carry flag to a duplicate of whichever bit got wrapped around. Yeah, so that's what I'm wondering, right? It sounds like we want this to be a 9-bit value, because it says rotate all the bits through carry. This is a 9-bit rotation, so it sounds like we want that, right? So then the question is for overflow. But I mean, the carry bit doesn't... So the question is it overflow if, like in terms of sign change, right? If it's a 9-bit value, let me bring up like a notepad. Let's say it's like this, you know? So this is carry, and then that's the most significant byte and the least significant byte. And now we rotate it, right? So this becomes... Now, if you consider the all 9 bytes, then the sign hasn't changed, if this is considered the sign bit. So Fred says exactly. And so in that case, overflow is not set. Yeah. So overflow... So overflow would happen if carry were not set and we did something like this, for example, right? So if this is considered the sign bit, if the carry flag is considered the sign bit, then this would overflow by doing the rotate. Because this would become 1, like that. Fred says, so I'm not sure about that. Yeah, I'm not sure either, because I mean, checking if a number is negative, usually you don't care about the carry. On the other hand, if you're using this, you're probably using it for... So Fred, would that be overflow, or would the next rotation be overflow when C wraps around? Well, so yeah, I don't know. You know, is this a negative number in the case of considering it as a 9-bit? It all depends on what's the interpretation, right? Okay, let me see if I can just find other docs. I might have some information in another document. I have like a bunch, so maybe the answer will show in here. What does A stand for again? Affected. Okay, that's not very useful. Okay, rotate left. Okay, rotate A, rotate left accumulator. A is equal to carry, comma A. That's been shifted, I guess. That's what this notation might mean. Yeah, so, okay, so if we consider B8 to be the carry bit, which might make sense, then maybe it's missing an XOR. I can kind of see that, right? That, let's say this were considered sign bit, right? If the carry is considered sign bit, then this would be overflow, because we went from positive to negative. And if we consider this bit 8 and bit 7. Another case would be the opposite, right? So this would also overflow, again, if we considered it as a sign bit. And in the other cases, we'd be fine, 1, 1, or 0, 0. So XORing these two would be overflow if that's the interpretation. So I don't know if that is the interpretation. I don't know how to find, maybe I can, I need like better docs. I need like an alternative that describes the instructions in a bit more. What about this guy? Is this guy any good? I haven't really looked too much at this one. 6809 assembly language programming. I wonder what year this one was published in. Does it say? (1981). So I was 2 years old when this book was published. So Fred says, is there a synthetic test ROM you could use to validate your implementation? Did somebody ever write one? That's a great question. I was actually wondering about that when I was writing my own tests. Vectrex test ROM. So apparently there are some test ROMs. I don't know what they are. I should definitely look into this. But I mean, this might just be like the test for the hardware or something that was made by the Vectrex company. And I'm not sure it's going to give me anything interesting at this stage, so I really have to look. I just saw something, ROMs and overlays. I was thinking about how I need to get overlays. Cool. That's super cool. Oh, there's even manuals. That's super cool. See here, Star Trek. Yeah. That's the Star Trek overlay. Okay. I'm gonna keep this link. I have a links place. ROMs and overlays. So what if I just look for 60? Oh no, sorry, I want to look at this book. This book might have it. Roll A. Like that. Okay, there are 4 hits. So ASLB and roll A together produce a 16-bit arithmetic left shift of the double accumulator D. ASLB shifts bit 7 of accumulator B into the carry, and roll A picks it up and places it in bit 0 of accumulator A. Yeah. Right. Yeah, because B is basically the low byte. So with ASLB, they're saying that they'll take the the bit 7 of B and put it into carry, roll A will pick up that carry and place it in bit 0 of accumulator A. So, right. Which doesn't answer my question about whether it interprets it as a 9-bit signed value. Let's see, maybe a few others. This instruction rotates the specified accumulator or the selected byte of memory 1 bit to the left through the carry flag. Consider rotating a memory byte using indexed addressing with 0 offset from index register Y. Oh, a nice picture. For example, suppose that PP is equal to 14, QQ is equal to 03 in hex. The contents of memory location 1403 are 2E16, so 2E. Data memory, program memory. And the carry flag contains 0. After the processor executes the instruction roll, Y, memory location 1403 will contain 5C, and the carry flag will contain 0. The overflow flag is loaded with the exclusive OR of bits 7 and 6 of the original operand. And there we have it. These bits are the same as those of the resulting carry and sign flags. So it's a printing error. It's like 2 errors, right? Like this should have been 6. I mean, it kind of, you can see, right? It's B7. They usually don't put a larger bit next to it. So this should be 6, and there's missing an XOR here. So both this and this, yeah. Okay, so I'm just gonna straight up do that. What I like to do that in that case, because I like to keep everything together, what I'm going to do is I'm going to make a result variable. I'm sorry for no, sorry. What I'll do is that. No, I need to overflow is equal to value before it's been changed. Bit 7 XOR value and bits 6. Okay, yeah, that's fine. So at least I have this other book I can use to double check things when I'm not sure. compute the result as the shift of this way with the carry. So value is the original value, so I can look at it to get the carry. And then finally, when I'm done computing my stuff, I can overwrite value with the result. Okay, I like that. Right, I need to write the other version for non-accumulators, for index registers. No, for memory values. Okay, so page opcode value, and then memory bus write PA value. Okay. Back into the debugger. Slowly but surely. Alright, so we're doing a roll of A. Rotate left of the A value, which is 0, so not super interesting. No carry, no overflow, no negative. And they didn't want to know about 0 in this case. Oh, they did. Forgot to take care of 0. And it's set to the 0 if all bits of the result are clear. Without caring about carry. That makes sense. Okay, here we are. So that's the case we saw before. This time 0 does get set. Okay, so here's something slightly more interesting, assuming we're doing B. No, we're not. So 73 is for A. So I never got anything but 0 so far in there, but it's all right. And now we get EOR A. So EOR, logical exclusive OR. Okay, cool. So I don't know if this is right, but it looks right to me, so let's go with that. Implement RL, rotate left CPU instruction. Okay, So next instruction is logical exclusive OR. Let's go take a look. EORA. Here we go. Exclusive OR. The contents of memory is exclusive ORed into an 8-bit register. Pretty straightforward. Just do an exclusive OR of the register with the memory value. Okay, looks good. Let's do that. This ERA, I think this is accumulator only because it's memory into accumulator. Yeah. So let's do a find in document. Alright, so where do I stick exclusive OR with? I think I have AND, so I'll just put it with AND. Hop AND, here we go. Put right after that. Case hop EOR 0 break, and we want to take these put them in here, grab these registers. Yeah, and we'll just delete that. What is it? What don't you like? Strange. Usually it formats even if it doesn't care, if it doesn't know what the function is. Here, let's try this. Unexpected token. Line 2, position 66. Ah. Must have hit a key before. There we go. My Clang format wasn't formatting the code because it was detecting an error somewhere at the top of the file. Syntax error. So I couldn't recover. Okay, so let's implement exclusive OR. Looks a lot like AND. Basically, the register gets can I do this? I think so. So negative and 0, usual fare. V is cleared. C is not affected and H is not affected. And that's it. So writing an emulator, implementing the CPU, is a bit of a chore and kind of blind work. I need to be able to double check what I'm doing. So what Fred suggested about looking for a test ROM is a good idea. Otherwise, I have to write my own tests, which I somewhat did, but it's a lot of work. What was I looking for again? It's this guy here, yeah. Okay. Exclusive OR of the value in A, which is 0. So now we're at rotate right A. So we did rotate left, and now we'll do rotate right. Let's find all the rotate rights. There are 5. We'll obviously put them next to rotate left. Case up, rotate right. Break. Then A and B over here, so. It's always the same pattern. Okay, let's take this guy. All right, rotate right. Oh, we're right there. Rotate right. Okay. Rotates all bits of the operand right one place through the carry flag. This is a 9-bit rotation. The 6800 processor also affects the V flag, but not this one. This book likes to talk about the 6800 processor, which is the kind of the precursor to this one. I'm going to need more water soon. Okay. Not affected. Set if bit 7 of the result is set. 0 is set if all bits of the result are clear. C is loaded with bit 0 of the previous operand. Right. And the carry goes into bit 7. So this one does not deal with overflow. Which is interesting. The sign can change, but I guess it doesn't make sense to be rotating right and worrying about signs. So, yeah, you'd only worry about that if you're doing 16-bit values out of rotating left. Yeah. Okay. Rotate right. So. take the value and shift it right by 1. And we want to OR the result. Oh, what did I do here? So that was wrong. I wanted bitwise OR. And here we want to take the CC carry, shift it left by 7, and OR it with this here. Yeah. The carry is going to be set to the original values 0th bit, calc 0 of the result, negative calc 0 negative of the result. That's it. So let me double check. I want to take the carry bit, shift it left 7, and then OR it with the input value shifted right by 1. So that's rotating the carry there. And the carry gets the original values bit 0. Yeah, looks good. And now for the versions with memory. Yeah, I'll just copy this. And then basically it's op rotate right here and here. All right, cool. Let's run our debugger again. Making good progress. Oh yeah. So this is the rotate right. Of A, which is 0. This is 70, so this is again of A. When I test these calls, it's always 0, so it's not super interesting, but it's okay. All right, so next one, LBMI. What is that, like long branch if minus, I think it is. And I already did the branching one, so this one should be a piece of cake. Yeah, it's a branch if minus. So these are all the long ones. I gotta remind myself what this means again. I'm gonna have to look at the doc. I'm just gonna go get some more water, so I'll be right back. All right, and I'm back. Okay. Fred, looks like it's just you and me right now. Okay. Man, I drink so much water. When I'm talking all the time. So long branch, LBMI. So what's the deal with the long stuff? Okay. So basically, looks like the idea is to use a 16-bit value. Okay, so my guess, because basically branching just means adding an offset to the program counter, but it's only an 8-bit offset, 1 byte offset. Like if I look for BMI and op branch, yeah, that's it. It's an 8-bit offset. And I guess the long branch, oh, I actually have some here, LBSR, long branch subroutine. Yeah, okay, so that's for a branch for subroutine, but normal branching, so I guess the only difference is that it allows you to specify a 2-byte offset. That's what it looks like. Extended range long branches. Yeah. I think that's all it is. Let's see here. Read relative offset 16. So what did I do here? Read PC 16. Okay, so it like reads 2 bytes. Does that make sense? So this here is a 5-byte instruction. Is that right? No, sorry, that's cycles. It's a 4-byte instruction. Yeah, okay, yeah, that makes sense. Basically, the first byte is going to be 10 in hex to say that it's on page 1. Then it's going to be this value to tell us which instruction it is. And then after that, 2 bytes make up the address, no, the offset that we want to apply. So I guess what I want is an op long branch. It's going to be very much the same as all of this here. BRN. Branch never. Branch never. BRN was 21. Okay, so they even have the same codes. Branch if higher. Why am I? Trying to understand why the ordering of these instructions is so weird. Anyway, but yeah, it looks like makes sense there. It's the same. 22 here is BHI, 23 is BLS. I wonder if I can take advantage of that somehow. I want these to be in order. I'll start with that. Let me just fix the order of these instructions. Okay, actually, do I have something to commit? I do. So I did implement rotate right and exclusive OR CPU instructions. Okay, so let's do just a little bit of reordering here. So 2A goes here, 2.6 there, 2B down here. D 23 to F just zoom out a little bit. 22 to E to C to 7. Oops. 2.4 and 2.5. So 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So those are all the branch instructions. What I'd like to do is take advantage of the fact that it's exactly the same thing for the long branching. The problem is that I have this like switch case 1 for page 0 and I have a separate one for page 1 here. All right, it's okay. We'll call this one op long branch. There we go. And the only difference will be that rather than this, we'll get a 16-bit relative offset and add it to our PC. And I suppose it's one cycle if the branch is taken. Take a look. 5 or 6. I don't trust this table. Five, 6. Branch instructions. What I don't get is why they're not showing that this is 3 or 4. What does this asterisk mean here? Okay, this talks about cycles here. Relative addressing. For all of these actually, hey, Cool in the Gang says, what's up, dude? What's up, man? Thanks for joining. So yeah, I think my information about the branching, adding a cycle, only is true for long branches. Here is cycle 1, 2, 3, 4, 5, and then there's if branch is not taken, we're done. If branch is taken, we get a 6th cycle. But for these ones, we don't get an extra cycle. It's always 3, which might explain why the tables, the tables that I've been looking at don't show anything special here for these branches. But if I go to, let's say, the long ones, they have 5 or 6. Yeah, Fred says on Game Boy extra time is only taken if the branch is taken. Yeah, that's what I understood as well, but it looks like that is only true for the long versions of the branch instructions, meaning 16-bit relative offsets. But for like 8-bit relative offsets, 1-byte relative offsets, it's always 3 cycles. So here is the actual, I have this document on cycles. It shows what every cycle does. Like here is the opcode fetch. There's an offset applied, a don't care cycle. Yeah, and it's like always 3 for the normal branch operations, and then it becomes... Oh, hey, Fred, by the way. I don't know if he wants me to say his name. Let me ask. You don't care? Yeah, so Fred, this cool in the gank is Simon. My lawyers will get you. I always have to ask, man. You know, you didn't put your name anywhere on your Twitch page, so I wasn't sure if you'd be okay with me saying it, so I always ask. So Fred is saying it's a clever name. I feel like I've missed a joke. Why is it clever? I guess I'm not clever enough. So then that means that this is not true, but it'll be true for the long branch. It's a trolley name, or a trolley. Like you mean like troll? Ganking is when you team up on people in MMORPGs. Okay. Okay, so let's shove this in here somewhere. Good old copy paste. So it's heavily discouraged. Yeah. So that's interesting. Hop long branch. There are 16 of these. Okay, so I should hit a long branch. So Simon, when you're playing when you're streaming your runs there, your speed runs, I heard the commentators calling you gank. Is that what they usually call you? They call you gank for short? All right, so here's the long branch that we got earlier. So it's a branch if minus, and it is minus. The offset is 156. Right, because it's cannot do a short branch because it's bigger than 128. So Simon says, sometimes cool, but I always put Gank as my name in Zelda 2. Ah, right, so that's why they call you that. Makes sense. So this will move me here, and then you get an extra cycle. Another long branch. This might be a loop. Yeah. Let me see what PC looks like. E537. Yeah, looks like I'm in a loop. Okay, so let's just keep going. This might actually be an infinite loop. So Simon says, last time during a commentary, a girl asked, should I call you cool or Gank? I said, you can call me Daniel-san and I'll call you Mr. Miyagi. You're such a flirt. Get all the girls. Okay, so it's not an infinite loop. We're not ABX. Awesome. So let me get that committed. I didn't think I was flirting. She's like a Tetris master. But can she play the Tetris master? She speedruns Tetris. That's cool. Yeah, I feel like just making a separate commit for when I reorganized all of these. Reorder jump instructions by opcode value. So Simo says, I noticed she was providing commentary for a race last week, so I offered to help. Do you use Discord? Like, you mean at work or in general? I've never used Discord. I know that we have someone at work who's installed it, and there's like one team I think that's using it. This is op long branch. Implement long branch. CPU instructions. So why do you ask about Discord? So man, I'm just tearing through these opcodes. So Simon says, it's just that it seems big on Twitch. Yeah, yeah, it's true. I have seen other channels saying, keep the conversation going on Discord. I guess it's all part of like building a community around the channel, right? So even when you're offline, people can go and talk about stuff, I guess, give ideas. So let's just see tonight. Implemented the complement, multiply, sex, rotate left, rotate right, exclusive OR, and a long branch. Oh, oops, I didn't mean to say jump here. I meant to say branch. So, yeah, Simo is saying that every game has a community. It's like Skype, but they have communities. So you can join the Zelda community, and next time you play Zelda, you can talk to other players at the same time. I mean, I guess, yeah, I guess, I mean, is it because, I mean, normally you have your conversations in chat, right? But I guess if you have multiple Twitchers playing against each other or playing together, you know, Discord provides you the kind of one-stop shop where everyone can chat in one place for multiple channels. I guess that's what they're going for. Which maybe makes sense for stuff like races where you don't even know who's gonna race. It can be different people, so it gives you this one place for the community. Yeah, so I just wanted to or they will post anyone up for a race and you don't have to have IRC open all the time waiting for a race to start. Right, because I guess you get notifications on Discord. On your phone, email, yeah, exactly. Okay. So, ABX. What's ABX? Add to index register. So I guess it adds to X. Oh, that's much more specific. Add accumulator B. into index into x. So it's really add b into x. I think I'm going to change this here. Add b into x. Yeah, a, b, x. Add b into x. Man, it must have really sucked to have only 3 characters per mnemonic. So where do I stick this special guy? Just noticing that I have instructions that don't take template arguments. I'll revisit that when I might use macros later. Okay, so add b into x. So what does it say here? Add the 8-bit unsigned value in b into the x register. That's it? Okay. Sounds good. Maybe x. So we just grab x plus equals b. Nice and simple. Perfect. I like simple instructions. Yeah, simple instructions. We're not getting paid by lines of code here. Yeah, I'm not getting paid at all for this. So another unhandled instruction, DAA, EA18. Yeah. So man, it totally looks like we're in Mindstorm. So Simo, I know you didn't hear this before, but right now the CPU is actually executing instructions in this range. It's like here is EA18, and in the Vectrex, that means that we're executing Mindstorm. So that's pretty cool, right? decimal adjust accumulator. Yeah, Mindstorm. Remember Mindstorm? The built-in game in the Vectrex? Like when you turn on the Vectrex, it's like a what's that called there? That game, Asteroids. It's this like Asteroids clone on the Vectrex. So it's called Mindstorms, and it's, you know, if you remember, you don't put in a cartridge and you boot it up, and it actually boots up Mindstorm. And I know here that basically in memory, the memory map says that starting from E000 to EFFF, that's Mindstorm, and then the second half, F000 to FFFF, is the BIOS. It's like all the BIOS routines, you know, like basically the routines that games can use to like set the to like pull the input, play music, set the reset the position, or set the position of the beam, the vector beam. All of that stuff is in the BIOS. And so for the longest time while I've been working on this, I've been in this address range, and today I noticed at one point, hey, we're now in this address range, which means that we've gotten to the point where Mindstorm has started, which is pretty cool. So DAA is decimal addition adjust. Decimal addition adjust. That sounds like an interesting. Oh Lord. So Fred says, oh Lord, that instruction is infamously complex to implement on Game Boy. Oh great, that's good to hear. In fact, there are some emulators that don't even bother with logic, they just use a lookup table. So what does it do? Accumulator A gets accumulator A plus CF MSN CF LSN. So most significant nibble plus the least significant nibble of whatever CF is, where CF is a correction factor, as follows. The CF for each nibble, BCD digit, is determined separately. Fred says Game Boy used it for game scores. Yeah, I was thinking that's probably what they're using it for here. Which would make sense if we're in Mindstorm. Okay, so the correction factor for each nibble, BCD digit, binary coded decimal digit, is determined separately and is either 6 or 0. So least significant nibble. It's funny how he writes nibble with a Y. Maybe that's either that's just an alternative spelling, or that's how they spelled it back in 1980. Or maybe it's a British thing. Yeah, Fred also guessed maybe British. Yeah, likely. Okay, so it says here the correction factor is either 6 or 0. For the least significant nibble, the correction factor of the lowest significant nibble is 6 if h is 1 or so this h is the half carry, or if the least significant nibble value is greater than 9. Okay. and the most significant nibble is going to have 6 as a correction factor. If the carry is 1, right? Or if the MSN is greater than 9, or MSN is greater than 8 and LSN is greater than 9. Fred says they put a Y in tire. Yeah, that's true. Okay, so the idea here, if I understand correctly, is that we've added some value, we've added something to A, and we need to correct it we need to adjust it so that it is a decimal. So, okay, so each nibble represents a decimal digit, and like for example, if we're at 9 in the low nibble and we add 1 and it becomes 10 in the low nibble, we want it to become 0 and then a 1 in the high nibble. I think that's the goal, right? Hence these checking for greater than 9. This here, H, is basically the half carry, which add will set if the third bit is set. And then carry is the 7th bit. No, sorry, half carry is if the third bit carries into the 4th, and this will be set if the 7th carries out. And for the most significant nibble, it's saying that if the most significant nibble is greater than 9, we need to adjust. It makes sense. Or if it's greater than 8 and the lower one is greater than 9. Because, all right, so this one here will adjust into the high. So let's say it's 10. This will become 0, and then the 1 needs to be placed into MSN. But why if it's greater than 8? Oh, because, right. Because if this is greater than 8 and that's greater than 9, that means that this will affect the MSN, and the MSN will also have to be adjusted because it will become greater than 9. That's right. This will make the next one, okay, the LSN greater than 9 will make the MSN be greater than 9, which means it needs to be adjusted as well. And then y is adding 6. What does adding 6 do? So now I can see what you mean about having a table. But I mean, I wonder if it's more about the fact that it's just much faster to just look it up in a table, you know, than it is. I don't know if is it about complexity? I mean, it's a bit complex, but this explanation is not too bad if it's right. Ah, for the flags. here, oh, there's more information. So here, like, this is okay. For carry, set if the operation caused a carry from bit 7 in the ALU, or if the carry flag was set before the operation. Okay. So you just have to be careful with the add. Description, the sequence of a single byte add instruction on accumulator A, either add A or add carry with A, and a following DAA instruction results in a BCD addition with appropriate carry flag. Both values to be added must be in proper BCD form. Each nibble such that 0. Okay. Anyways, basically each one is in 0 to 9. Yeah, so the Game Boy has half carry, so does this processor. And I am setting it, hopefully correctly, in both add and add with carry. And it does participate in here. So multiple precision additions must add the carry generated by this DA into the next higher digit during the add operation immediately prior to the next DA. Right. Okay, so they're saying if you want to do a multiple precision value, so more than just 1 byte. Okay, well this looks like super fun. Let me take a stab. Oh, what just happened? Okay, I'll stop the debugger. So there's DAA. Is that all? Is there like another? No, it's just for A. It's another one of those inherent single purpose instruction. So Fred says, for what it's worth, I did not successfully implement this instruction. I tried a bunch of stuff, then looked at emulators, and a bunch got it wrong too. Also, documentation was very sparse. So in the end, I used the guy's pseudocode. Yeah. Too big for you're trying to paste the comment that you wrote. Yeah, this is the kind of thing where having a test ROM would be really awesome. What I'm thinking of doing is what I might do, because if I can't find a good test ROM, I don't really feel like writing a bunch of tests. What I've been pondering is I don't really want to look at other emulators. You know, I don't want to look at other emulator code. That's, you know, I don't want to be influenced too much. But what I was thinking of doing is kind of taking another emulator that correctly emulates the Vectrex. There are like 2 or 3. So taking, let's say, the best one with the simplest code and trying to like seeing if I can integrate their CPU into my code base without like looking at it too much, and then making it like a second CPU. And what I want to do is I want to run mine and run it, so have it basically implement the same interface as mine, and compare. You know, am I getting in the same? Are the registers the same? I might have even, you know, I mean, ultimately I would do it all in one go, right? Like have maybe 2 copies of all the hardware, like say the memory and all that, and then compare them. Or, you know, just run my emulator with one, run it again with the other, and compare the results. So something like that. It's a bit similar to what I did with for the NES emulator, but in the case of the NES emulator, I didn't integrate the code into mine. I made mine follow the same trace output format as another NES emulator and compared those. But here I'm thinking of going a bit further, because it was always tricky with comparing trace output because of cycles. I would not always be in the same cycle and all that, so it made it a bit messy. So I'm thinking if I just have the CPU code and I can swap between the two, I'd also be able to see if it's, you know, oh yeah, interrupts. Yeah, exactly. And you know, what I learned was that, yeah, you know, it doesn't have to be super accurate, right? And so there's like slight differences between emulators, and it's okay. So that's it. Having the CPU of another emulator as a point of reference will help me validate some of my code. But yeah. So I'm looking at the time and it's actually getting late. So what I think I might do is stop here. And I'll think a little bit about this guy and maybe tackle this on Wednesday if I stream on Wednesday. So I'm just going to push what I've got. Did a lot of work tonight. Pretty cool. So now we're ostensibly in Mindstorm. All right, man. So thanks for hanging out, and I'll see you tomorrow. Good night.